Good morning, class. So I hope you finish your quiz one. It's simple and easy questions. Okay, I will double check for those who have submitted the question paper. I will let you know for only the name who didn't pass up. Okay, I will post it. So I will name up the student didn't pass up. If your name is not in the name list, that means we have submitted and received. Okay. Let's continue our lecture to this example 2. So last week we have studied how to calculate the PDF and also the CDF and the smoothed kernel distribution or smoothed kernel density. To propose another method that is without use the table, and I calculate that as simplified by the piecewise function. Okay, so you may try this method to save your time. Okay, here we go.
Number 12. Given the 5 observation that is here, determine each of the following estimate of kernel smoothed distribution function at 150. For the following empirical estimate, part B, the kernel distribution estimate based on the uniform kernel with this bandwidth, B is 50, and part C, for the kernel distribution estimate based on the triangular kernel with bandwidth which is 50. So this is to find the value of this kernel smoothed distribution at 150. Solution for example 12. Let x be the random variable of the given data. Let nxi be the number of xi. Then we have the following. So we try to place all the data given, which is 82, 126, 161, 294, and the last is 384. So the frequency, all the data are 1. Therefore, the probability of each observation here is 1 over 5. Part A, we have to find the empirical estimate of this. So obviously, for empirical estimate, that we have to find the probability that this x is less or equals to 150. So we have 2 observations that is less than 150. Therefore, the probability is 2 over 5.
Okay, class. For part A, I purposely put this question, and this one actually we have learned in chapter 1. There's a very simple calculation for this just empirical estimate of this CDF at 150. Okay, so this one you no need to use the kernel formula or whatever. Just simple. Okay, just take the number of observation that which is less or equal to 150, okay, divide the total sample, you will get the answer.
Part B. Let x is uniform distributed on this interval where the bandwidth is 50. So in order to solve this problem, that we need to calculate what is the kernel distribution function at 150. So to solve this problem, I'm not going to use the table like in example 11. So I'm going to use this formula to calculate. So I have to calculate this in terms of piecewise function. So for the first range here, that is when the x you take 150, which is less than the xi minus the b value. The value is 0. And for the second interval here, that when the xi minus 50, which is less or equals to the x value, that is 150, and the xi plus the b, so the value is become the x, which is 150, minus the xi. Xi is our observation, and minus the 50 divided by 2 times 50. And for the last interval here, that x, which is 150, greater than the xi plus the 50. And this is 1. So next I'm going to rearrange this piecewise function, that this xi is always greater than 200. And for the second interval here, this xi is greater than 150 minus 50, that is 100.
Hello, sir. Cannot hear.
And for the last interval,
Since when?
Since the new one, the 0 200 minus xi.
Okay, I have to upload again. You hold on.
and this is 1. So next I'm going to rearrange this piecewise function, the xi. Xi is our xi is always greater than 200. And for the second interval here, this xi is greater than 150 minus 50, that is 100. And this xi is always less than or equals to 150 plus 50, that is 200. So the value here is 200 minus xi divided by 100. And for the last interval here, this xi is strictly less than 150 minus 50, that is 100, that is 1. When the observation is less than 100, that is, this kernel distribution is 1. And 100. So I'm going to take 1 over 5, this probability, times this k value, which is 1, plus the observation value lies between this interval, that's 100 to 200, that I have these two values. So that means I'm going to take this probability times the k value. So the probability times this 200 minus the first observation, that is 126, divided by 100, and for the second value in this interval, there is same probability times 200 minus 161 and divided by 100. So all the observation greater than 200 will become 0. So these two values, which is greater than 200, therefore is 0. So I will take this probability 1 over 5 times 0. So this result will give me 0.426.
Okay, class. Now, for here, you can see I simplified the piecewise function. Okay. Now, you have to refer to this formula. Okay. So you please look at the x value. This x value is 150. Okay. The xi is observation. Okay. So you have to substitute all your x value. Okay, so I try to convert this piecewise function in terms of xi. So when I substitute my x as 150 inside here, then this piecewise function become in terms of xi. Okay, so you can see like x is a 150. All the x here, okay, you substitute as a 150. Okay, so you will have this. Okay, you will have this. You can see this piecewise function now. There's no more x, right? Because you substitute x is 150. So all in terms of xi. Now you rearrange the inequality. Okay, so if you rearrange the inequality, that you can see this is the result. So that means now we are talking about the xi greater than 200, xi bounded from 100 to 200, and so on. Okay, so then you know that this xi is referred to our observation. So whatever the observation falls on this interval, then the k value is 1. In the second interval here, the k value is here. In this interval, the k is becomes 0. Okay, so this is much more faster than you plot the table. Okay, so the next should be no problem that you can calculate this, right? Okay, so you just by taking the formula, you can calculate. Okay, so I believe you have no problem to calculate this. Okay, so the answer is
0.426.
Okay, so this is a way how you calculate, right, faster. So now I move to part C, also the same. The part C actually is for the triangular. Okay, so you please don't mute my mic because when you mute, you won't Okay, the sound won't come out. Please don't mute. Here we go.
Part C. Let X is triangular distributed in this interval where 50 is the bandwidth. So we have to find this value for this kernel smoothed distribution function at 150. So we have to calculate for this kernel distribution function at 150. So we use the same method like in part B, that is, we try to use the formula instead of using the table. So this is the formula I'm going to use. So this will be equal to this piecewise function, that for the first interval that the x will take 150, which is greatly less than the xi minus 50, so the value of k is 0. The next interval will be the xi minus b, that is 50, less or equals to the x value, which is 150, and less or equals to xi. So the k value will be b, that is 50, plus x 150, and minus xi squared, divided by 2b squared, that is 50 squared. So for the third interval, that this xi is less or equals to the x, which is 150, less or equals to the xi plus 50. So the value of k is 1 minus b minus x 150 and plus xi squared, divided by 2 times b squared. And for the last interval, that this x, which is 150, greater than the xi plus b, that is 50. So this is always is 1. And next, I'm going to rearrange this result. Then we will have this 0, and this xi is always greater than 200. And this is equals to 200 minus xi squared divided by 5,000. And the interval will be this xi is always greater than 150 and always less or equals to 200. And for this result, this will be 1 minus xi minus 100 square and divided by 5,000. And the interval will be x is always greater or equals to 100 and less or equals to 150. And the last result is 1, that is when the xi is strictly less than 100. So for xi is less than 100, we have one value which is less than 100, so this will be equal to 1/5 times this k value is 1. And for this range here between 100 to 150, I have one value that is 126. So again, I will take this probability times this value, that is 1 minus the xi value is 126 minus 100 square, and divided by 5,000 and plus the interval here that is between 150 to 200. I will have this value 161. So again I will take this probability times this value, that is 200 minus the xi value, that is 161 square, and divided by 5,000. And whatever value is more than 200, the k value is 0. So therefore, this is 0. So simplify this, I will have 0.4338.
Okay, so we use a similar method like just now, part B. We try to simplify this piecewise function in terms of xi. So when you substitute your x as a 150 into the formula, then you will have this. Okay, then after that you can refer to the data, see whether the data falls on which interval. Okay, then you just use the result and multiply the probability. Now here I want to highlight class. So please take note and pay attention. Now this 1.5 is overlap, right? So doesn't matter. You can take either one is kick out the equal sign, or you just leave it like that, no problem. Because when it's 150, either you choose this piece or this piece, the result still the same. Okay, I repeat that. If your xi is 150, whether you put here or you put here, these two will give the same result. Okay, or you kick out one of these, the equal sign, no problem, or you just leave it. Okay, so do not worry about the equal sign, okay, because this is continuous. Remember, this kernel distribution is actually, the original problem is discrete. Okay, we smooth the graph, become continuous. Okay, now we have done this example 12. Okay, so do not forget you have to check in your attendance. Okay, I share the attendance